Good afternoon, dear participants of the Conference of Climate Science Agriculture for Asia 18th TSAE International Conference. My study is about improving thermal performance of the solar parabolic through collector using internal finite structure. I am Omajan Urishev. I am an assistant professor at Fergana Polytechnic University. Fergana State Technical University, exactly. Just uh, the solar collector is a device that assists in converting solar radiation into the thermal one. The parabolic through collector is regarded as an exceptional solar collector for the medium temperature range at around 150 to 400 degrees C heat demand. Nowadays, uh, enhancing thermal performance of solar parabolic through collector has attracted many researchers. Along with the other component, including parabolic mirror, metal support structure, and tracking unit assembly, and the absorber tube, and it's called also receiver tube, also as known receiver tube or heat collection element, is one of the primary function part of the solar parabolic through collector. The main reason for this is that the efficiency and the performance of the solar parabolic through collector system highly depend on the design and the effectiveness of the absorber tube. Therefore, numerical method including half insulation receiver, cavity receiver, vacuum outer shells, buffless, artificially roughened sinks, selective coating, something like that will use it in an effort to enhance the heat transfer potential in the receiver tube of the parabolic through collector. Simply, we can call the receiver tube as a heart of the parabolic through collector. In our study, first we have started with the material selection for the receiver tube. We have chosen three different material: aluminum, copper, is four different material: aluminum, copper, iron, and steel. As you can see, this schematic diagram of the parabolic through collector in the first graph, and also the geometric dimension of the receiver tube is demonstrated in the table 1, you can see. And we have used electric analytic method for heatless evaluation of the absorber part, and we have demonstrated the outlet, the mathematical equation to define the outlet temperature variation of the um, absorber tube. As you know, the solar radiation is transferred into the for heating the fluid, heating the absorber, and for the radiation. And we have used balanced equation, and we have found out the outlet temperature of the uh, absorber tube. And to simulate this receiver tube of the solar parabolic through collector, we have used Thomson multiphysics. And in the next page of the presentation, you can see the surface temperature variation of the receiver tube with a different material. As you can see, the maximum temperature variation is observed with the steel receiver tube, because the steel has a less thermal conductivity compared to the iron, copper, and the aluminum. And we have simulated this absorber with two different inlet velocity, 0.05, 0.07 kilogram over second, and the minimum temperature variation, surface temperature variation, is observed with the copper one, you can see, because the copper has a better conductivity, thermal conductivity, compared to the other material. That's why copper, I mean the transferring the more heat into the heat transfer fluid. In the next part, we have just analyzed the surface and heat transfer temperature variation of the receiver tubes. In the first graph, you can see the surface temperature variation of the receiver tube with the different materials at different velocity, to different velocity. In the next graph, the temperature variation of the heat transfer fluid at different mass flow rates with different material is demonstrated. As you can see, the heat transfer fluid temperature, maximum heat transfer fluid temperature observed with the copper receiver tubes. As I have mentioned, the copper has a better conductivity compared to the other material. However, the steel one showing the heat transfer fluid in steel receiver tubes showing the less value compared to the other material. And in order to enhance the performance of the parabolic through collector, we have just focused on the geometric change of the receiver tubes. As you can see, we have selected simple receiver tube and the finite receiver tube, and we have modeled these two different receiver tubes in console mount physics. Thermophysical properties of the material, solar variation of the solar radiation during the day, finite element analysis we have used to solve the three-dimensional Navier-Stokes equation for that system. And we have just interpolated the solar radiation. You know, the solar radiation is variable during the day. That's why we have interpolated these values depending on the time. Let's turn to the next page of the presentation. Just in this page of the presentation, we have demonstrated the variation of the surface temperature of the receiver tubes over 7 hours. As you can see, the surface temperature of the receiver tubes, finite receiver tubes, has demonstrated higher values compared to the simple receiver one. And variation of the temperature and useful energy gain of the simple and finite receiver tube, you can see. In the first graph, you can see the temperature variation. You know, the temperature variation of the finite receiver tubes much more higher than the simple one, and also useful energy gain of this finite receiver tube is also higher compared to the simple one, and thermal efficiency of the simple finite one is also higher compared to the simple one, you can see. I mean that by analyzing this graph, we can see the how can I say it? Applying the finite structure for the receiver tube is the exceptional option to enhance the thermal performance of the solar parabolic through collector that we are suggesting. That's why we are suggesting the geometric change for the receiver tubes. And in conclusion, a numerical model of two different receiver tubes are modeled in console mount physics software. And surface and outlet temperature variation of the receiver tubes and useful energy gain also are investigated. Maximum outlet temperature of the heat transfer fluid, finite and simple receiver tubes are 635 Kelvin and 620 Kelvin respectively. Furthermore, useful energy gain thermal efficiency of the receiver tubes are determined. Useful energy gain through the finite absorber tube was about 1400 watt, while it was 1000 watt in simple absorber tubes. Thermal efficiency 0.6, 0.4 for finite and simple receiver tubes. It can be concluded that finite receiver tube showed better performance compared to the simple receiver one. This is because finite structure significantly increased the heat transfer surface area to the heat transfer fluid. Thanks for your attention. That's all.